welcome Jamie. Got it. Jamie, Gabe, or Gabe. I don't know how to pronounce it. So we are back to classification of C-star algebras, but it's kind of new approach, which at least I find much more exciting than the previous one. Please, Jamie.
Thank you very much. And thanks for the introduction and the invitation. So what I'm going to talk about is a new approach to classifying C-star algebras, but actually it's more than that. I would say it's even a new approach to really understanding nuclear C-star algebras in general, and in particular, it's a way of extracting information from von Neumann algebras and pulling it back to C-star algebras, and that's really what I'm going to try to focus on today. Is not so much because I imagine that a lot of people have already heard a lot of talks about classification of C-star algebras, and so I won't go too much into the details of just classifying C-star algebras, but more what are the new techniques that I used to do this. So I should also mention this is joint work with Jose Carrion, Chris Schaffhauser, Aaron Tiquisis, and Stuart White. So let me first remind you of what is a nuclear C-star algebra. So first of all, let me just introduce some notation here that I write fin A comma A to mean the set of completely positive maps that factorize through finite dimensional C-star algebras. And a C-star algebra is nuclear if the identity map can be approximated in point norm topology by maps in this set fin A comma A. So this is equivalent to having a unique tensor product with any other C-star algebra. So often the first definition I gave is called the completely positive approximation property. And nuclear C-star algebras were, I think, more classically said to be the ones that have a unique tensor product with any other C-star algebra, but these are known to be equivalent. So as I mentioned before, a lot of this talk will also focus on the relationship between C-star algebras and the von Neumann algebras. And there are similar notions in von Neumann algebras. So a von Neumann algebra is semi-discrete if the identity map can be approximated in the point ultra-weak topology by these maps factorizing through finite dimensional C-star algebras. And another very closely related notion is that of injectivity, which well, using work of Bill Arveson, this is equivalent to saying that if you embed M into B of H, then there is a conditional expectation going back to M. Of course, for those who know what injective really means, they would know that I'm cheating a bit here by using Arveson's theorem, but this is a nice little clean way of explaining it. So let me start out with mentioning a very, of course, very well-known result of Alan Kohn, which is, and I will be mentioning and using this result over and over and over again throughout the talk. So this is that for von Neumann algebras, being injective and semi-discrete are equivalent conditions. And moreover, if my von Neumann algebra has a separable predual, then these are also equivalent to the von Neumann algebra being approximately finite dimensional, AFD, or often also known as hyperfinite if the von Neumann algebra is finite. And this means that I can find a sequence of finite dimensional C-star subalgebras whose ultra-weak closure is equal to all of M. So really, if I know that my von Neumann algebra is injective, then I can actually write it as an increasing union of finite dimensional C-star algebras. So I'm going to use this theorem over and over and over again, and I expect that people know this theorem well. So hopefully whenever I say Con's theorem, you will know that I'm referring to this one. Of course, Con has a lot of theorems, but this is the one I will be referring to. So let me just try to explain maybe more classically how one would extract information from a von Neumann algebra back to a C-star algebra in a very classical setting here. So if I've got a C-star algebra A, then it will always have a so-called universal representation, which is just take the direct sum of all GNS representations. And the induced von Neumann algebra that you get from this, I'm going to just write this as the image and then take the double commutant. This is going to be canonically isomorphic to the double dual of the C-star algebra, so isomorphic as Banach spaces. And of course, it's easy to see that that the weak topology on A, ultra weak topology that comes from the double dual. So an easy lemma just to warm us up on how would one extract information from von Neumann algebras back to a C-star algebra is the following result, that if you've got a double dual which is semi-discrete, then the C-star algebra was already nuclear. So let me just sketch the proof very quickly. So it's easy to see that this set of completely positive maps that factorize through finite dimensional C-star algebras is a convex set, and therefore the point norm closure and the point weak closure will agree by the Hahn-Banach theorem. So it's enough to show that A is nuclear. It's enough to show that the identity map is contained in the point weak closure of this set. So by semi-discreteness, we know that the identity map on the bidual is in the point ultra weak closure of maps factoring through finite dimensional C-star algebras. And by working a tiny bit, it's not so hard to show that this also implies that the identity map on A is in the point weak closure of this set. So this is a classical way of extracting information from the enveloping von Neumann algebra back to the C-star algebra. And often these type of arguments with the bidual will somehow relate to the Hahn-Banach theorem. As a corollary of this, it follows from, or corollary of Con's theorem, it follows that a C-star algebra is nuclear if and only if its double dual is injective. So remember that injectivity was equivalent to semi-discreteness, which implies nuclearity, and it's not too hard to show using, again, Arvison's extension theorem that a nuclear C-star algebra has an injective double dual. So this is a very important result in C-star algebras, and for instance has a very, very nice consequence, which I haven't written down on the slide, which is that taking quotients of nuclear C-star algebras are again get a nuclear C-star algebra. And even now, 45 years after this theorem, we still don't have an easier way of showing that nuclearity passes to quotients other than going through the double dual to get there. So we really, at times when we study C-star algebras, we need to go through these larger von Neumann algebras to get to where we want to go. So what the problem with the bidual or the double dual is that it's just in general a beast. It's very hard to really extract information from this von Neumann algebra back to the C-star algebra, and therefore it's hard to use it for a lot of things. But what I want to try to give you is now a different type of von Neumann algebras where we can again pull back information to a C-star algebra A in a somewhat similar way. So in order to do this, let me first set up some notation that we will be using for the rest of the talk. So if I've got a C-star algebra B, which I will always assume that it has some nice fixed tracial state, then first of all, I can construct the so-called ultra power of B. So this is the norm ultra power. So I fix a free ultrafilter omega on the natural numbers, and then I look at the bounded sequences, norm-bounded sequences in B, modulo those that tend to 0 in norm along my ultrafilter. So really what you should imagine is I've taken my C-star algebra B and then I've kind of blown it up to a much larger C-star algebra. But one thing that I want to just plant in your minds is that this C-star algebra still looks a lot like B. It is a blow up of B, but it still has a lot of the same properties as B. And very often we are very happy if we can describe B in terms of, or very often we can describe B in terms of this B omega. So we also have a tracial state on B omega, which comes from the one we will fix here. And it's just given by taking a sequence of elements and just looking at the limit of evaluating it at tau and taking the limit along the ultrafilter. So this will give us a tracial state on this C-star algebra B omega. Another piece of notation that I just want to fix now is that whenever I'm in this situation, I can look at the left kernel of my trace, and this gives me a two-sided closed ideal in B omega. So I'm just looking at all elements in B omega, where if I look at BK star BK, evaluate it at the trace and take the limit along omega, I get 0. So there's a very classical result, and I think that it's more or less folklore, which says that if I take this C-star algebra and I quotient out by this ideal, I don't just get any C-star algebra, I get a von Neumann algebra. So I get a von Neumann algebra, and moreover, this trace that I have induces a faithful normal tracial state on this C-star algebra quotient. So really what I've got is I've got a tracial von Neumann algebra. So I've got a von Neumann algebra with a specified trace. And you can do this for any C-star algebra with any tracial state. You will always get a von Neumann algebra by doing this construction. So without going into too many details, you can actually identify this von Neumann algebra pretty concretely as being the von Neumann algebraic ultra power of a certain von Neumann algebra. And which von Neumann algebra is it? It's just the von Neumann algebra generated by the GNS representation of the trace. So you take, whenever I write something of this form, I mean that I take the GNS representation and then I take the induced von Neumann algebra. So this quotient here is actually a nice von Neumann algebra here that we can work with.
Just a second, I just want to ask a simple question. So in the definition of B omega, you were dividing by the things which had norm limit to 0. So in fact, you were dividing by something quite small, if I understand. So then you have to divide by more in order to get the von Neumann algebra. Yes.
Exactly. Okay. Yeah. Okay. Yeah. So okay. the thing is that this B omega really has a lot more of the C-star structure. Right. It's huge. It's very, very big, but it has a lot more. It looks a lot more like B than the quotient will do.
Okay, I understand perfectly. Yes. Okay.
But I'm very glad that you asked, because this is really part of the point here, is that the B omega looks a lot like B, but if I take this quotient of it, I actually get a tracial von Neumann algebra. And this is really what we want to use. So let me move on to almost the same setting as I had before. So now I assume that my C-star algebra is unital. And I also want to assume that it has no quotients of type 1. Essentially, I just want to know that all of my induced von Neumann algebras are type 2-1. I want to work with 2-1 von Neumann algebras. That's why I am making this assumption. I also want to fix now a separable nuclear C-star algebra with a faithful tracial state. So now a corollary of Kuhn's theorem from before is that I can always find a star homomorphism from A to this quotient that I had before, so this von Neumann algebra, which is a trace-preserving star homomorphism. So let me explain why this is true. So first of all, my C-star algebra B having no type 1 quotients, as I said, all I really care about is that this induced von Neumann algebra, this quotient, is a type 2-1 von Neumann algebra. And this is ensured by this condition. So now, if I look at the von Neumann algebra of A, so my C-star algebra A that I want to map out of, if I look at the induced von Neumann algebra by the GNS representation of the trace, I get an injective von Neumann algebra with separable predual, because A was nuclear and separable. So that means, by Alan Kuhn's theorem from before, that this is actually a hyperfinite von Neumann algebra, or an AFD von Neumann algebra. So I can write it as the ultra-weak closure of a limit, an increasing limit of, or increasing union of finite dimensional C-star subalgebras. Now, anyone who has done a basic course in von Neumann algebras will know that that you can divide projections in a 2-1 von Neumann algebra, and therefore it's easy to construct a star homomorphism out of this union of finite dimensional C-star algebras, which does the right thing on the induced trace. So we've got an induced trace on this von Neumann algebra, and we can find a trace-preserving star homomorphism from this union of finite dimensional C-star algebras. And now we can just extend this star homomorphism to the entire von Neumann algebra and restrict back to A. And then I've got my star homomorphism that I wanted up in the theorem here. So just before I move on, I just want to highlight something, because people who have seen just a tiny bit about classification of C-star algebras, who know of George Eliot's classification of approximately finite dimensional C-star algebras, will know that these are this was the original class of C-star algebras classified by K-theory by George Eliot back in the 70s. So these are the C-star algebras that can be written as an increasing union of finite dimensional C-star algebras. And what is going on in this new approach to classification, we don't have any inductive limit structures or anything like that, except that they are actually there. They are hidden in this proof. This is where we've got these finite dimensional inductive limit structures. We actually have them hidden by Kuhn's theorem in these induced hyperfinite von Neumann algebras that we've got. And this is really the starting point of everything we want to do. So we've got...
Wait a second, I have a question here.
Yes.
Which is that the right-hand side, which is B omega over the ideal, as you said, it is the ultra product of the original von Neumann algebra that you get without that. So I mean, this looks like related to this fact, which I had, this question I had posed in my annals paper about the approximate embedding, because I mean, at this point you are just needing an approximate embedding.
Yes. That's very true.
Yes.
I could have just made do at this point with an approximate embedding. And I always have such an approximate embedding, of course, because my induced von Neumann algebra here was injective.
Exactly. So in a sense, I mean, there you are not using the full power. You are just using the approximate embedding, which is much less, of course. Yes.
That is true. I should mention that I later on I won't actually be explaining why, but later on I will be using it more heavily because I also need this embedding to be unique in up to unitary equivalence. Yes, yeah. So I was planning on sweeping that under the rug, but everything else I'm going to be mentioning, I will be actually needing that A is nuclear. But you're absolutely correct that at this step, all I needed was to know that your induced von Neumann algebras are satisfy the Kohn-embedding theorem or the Kohn-embedding conjecture. Sorry.
Yeah, sorry. No, it's not even a conjecture. It was a problem from the start.
Yeah, yeah, yes.
Yeah.
Okay. So now what we've done is, we've taken two C-star algebras, assuming very, very little on them. I've only assumed that that I've got some nuclearity here, which, as Alan Kuhn just said, we don't actually use that heavily here in this particular result. But from this, we've produced a trace-preserving star homomorphism between my C-star algebra A and this induced von Neumann algebra. So that brings me to my next question, which is, when can we produce a star homomorphism from A to B omega, which is trace preserved? And of course, the best question would be to remove this omega and just ask, when can I find a trace preserving homomorphism from A to B? But for now, let me just focus on how to go from A to B omega. Because remember that B omega still looks and behaves a lot like B would do. So very often we're happy just to have a homomorphism from A to B omega that is trace preserving. So one can actually reformulate this, not quite reformulate, but at least a related question to this by using the theorem from before, is that if we know that we've got this star homomorphism down here, which is trace preserving, then really what we're trying to solve is a lifting problem. So we're trying to ask, when can I lift this star homomorphism to a star homomorphism from A to B omega? And anyone who's tried to lift star homomorphisms to star homomorphisms will know that this is a fool's errand. This should be more or less impossible to do in general. There's just, unless we put a lot of extra assumptions on the C-star algebra A, there should be in general no way of just lifting a star homomorphism from the quotient and up to this bigger C-star algebra. So it would almost be foolish to even try to do this. But luckily enough for us, Chris Schaffhauser didn't think that this was such a foolish thing to try, so he just gave it a shot, and he was actually able to show that if B and the trace are very well behaved, so for the experts in the room, let me just say what I mean by this is that the C-star algebra B should have strict comparison with respect to this trace. I don't want to go into details what that means, but examples where this is the case would be for any unital AF C-star algebra which has a unique tracial state, or it could also be an irrational rotation algebra. It could also be the Jiangsu algebra, if you know what this means. And there are other nice classes of C-star algebras that could be this very well behaved. But then what was it that he proved? He proved that it actually just suffices to find a lift of this star homomorphism in KK. So it's enough to find a KK element from A to B omega that induces the KK class of this star homomorphism phi. Still assuming, that A is nuclear and all the other things that I was assuming before, which was still fairly minimal assumptions. So let me just say more precisely what it means. It means that, because it's actually a bit stronger than what I just said, is that any KK element that lifts this star homomorphism in KK theory can actually be induced by a star homomorphism that lifts this star homomorphism here. So even having the same KK class. So there's both an existence and uniqueness result here. And this is really where the magic happens. Well, of course, the first part of the magic happened with Kahn's theorem, and then the second part is Schaffhauser's theorem here to use KK theory to extract this information that we got on the level of von Neumann algebras and lift it back up to the C-star algebras. So unfortunately, this is still a bit hard to use because KK theory is hard to deal with. And this is where the universal coefficient theorem, the UCT, will come into play. So let me just quickly remind you, the UCT, we say that a C-star algebra A, separable C-star algebra, satisfies the UCT. Whenever I plug in a second C-star algebra D in the second coordinate, then the KK group fits into this short exact sequence where we've got homomorphisms on K theory and a certain X group of these K theory groups. So really what this means, morally, you could say, is that the UCT ensures that KK theory can be determined by K theory. And I can't mention the UCT for nuclear C-star algebras without mentioning the big open problem in the area, which is, do all separable nuclear C-star algebras satisfy the UCT? Short answer is, I don't know. Every single nuclear C-star algebra we've been able to write down satisfies the UCT by deep results, for instance, by Rosenberg and Schockert and Jean-Louis Thu. But in general, it's an open problem, still bothering a lot of researchers in the area. But this talk will have nothing to do with the UCT problem. I just wanted to mention. So what can the UCT do for us in this case? It can actually simplify the problem from before. So it was enough to lift this map in KK theory, but so I've just written the same theorem that I had before. But now, if A satisfies the UCT, then it's actually enough to lift it in K theory. So we've got a lifting problem that we got from studying the Neumann algebras, and now we combine it with K theory to get this lifting problem. And if we can lift it on K theory, then we can actually we can find a star homomorphism that induces the same map in K theory and lifts this homomorphism from before. So this is really what Schaffhauser's method is giving us. So just to take because I've bombarded you with a bit of information now and some tricks. So what should be your key takeaway so far from what I've said? So under the same assumptions that I had before, so I had a separable nuclear C-star algebra A and a C-star algebra B, and they both have some specified trace. Then finding a trace preserving star homomorphism from A to this B omega breaks into two parts. So the first part is about tracial von Neumann algebras, which was to find a trace preserving star homomorphism from A to B omega modulo this ideal, so that we get a tracial von Neumann algebra down here. And then we use KK theory to find a lift of phi in KK theory, and that will ensure that this phi actually exists. And the first part of this problem, that we broke into two parts, the first part about tracial von Neumann algebras, we solved using Kahn's theorem, and the second part we solved using Chris Schaffhauser's method, or of course the entire method was Chris Schaffhauser's, and then using the UCT to translate it into something about K theory that we can then solve. So let me try to give you an example of where this was used. So this is, I'm going to give you Chris Schaffhauser's proof of the Tigrices-White-Windsor theorem, which was the first time that this method was really used. So the Tigrices-White-Windsor theorem says that if A is a separable nuclear C-star algebra satisfying the UCT, then if A admits a faithful tracial state, then A is quasi-diagonal. So let me try to sketch the proof that Chris Schaffhauser gave of this. So I'm going to give you a slightly modified proof than what Chris did, but it's essentially the same proof. So first of all, from work of Voiculescu, we know that when A is separable in nuclear, then A is quasi-diagonal if and only if A embeds into this such a B omega for an AF algebra B. So this follows very easily from work of Voiculescu. I guess I also need the Troyeffer's lifting theorem because I want to assume that A is separable in nuclear, for otherwise this is not true. So this is really what I want to verify. So I've actually related my question about quasi-diagonality to a question of finding a star homomorphism from A to B omega. So now it looks a lot like what I was talking about before. So now let me try to give you Chris Schaffhauser's proof of this in a slightly modified version. So first of all, there is an induced homomorphism from the K0 group of A to the real numbers induced by the trace, which is just given by evaluating evaluating a projection at the trace. So this gives a homomorphism. Now, I would say it's almost an exercise. If you know a bit about K theory and AF C-star algebras, you should be able to construct a simple unital monotracial, so unique trace AF C-star algebra B, which is not type 1, where the K0 group of B is contained in the real numbers and contains the image of this map from before induced by the trace. So I'm using some K theory here, but this is not the hard part of the proof. So now we go through the machinery from before that I was highlighting. So we find a star homomorphism from A to B omega modulo this ideal. So in this case, it's actually isomorphic to R omega. So R is of course the hyperfinite to one factor. So we find this star homomorphism that is trace preserving. So now we want to lift this to a homomorphism in K theory, and really by how we chose this AF algebra B, there will be a canonical lift. Is because I basically built my AF C-star algebra to have an encoded lift. So that's the whole idea, is that if I take the composition, I take K0 of A, so the map induced by the trace becomes a map into K0 of B, which then maps to K0 of B omega. And this becomes a lift of the map from K0 of A to K0 of this 2-1 factor. So this map from K0 of A to K0 of the 2-1 factor, which is just the real numbers, is just the map induced by the trace. So by combining this, it's not hard to see that this composition up here was a lift of the one I had down here, which means that by Schaffhauser's theorem from before, we get a star homomorphism from A to B omega that preserves the trace. And now this implies, because it's easy to see that this phi is faithful because my trace tau A was faithful, and therefore my C-star algebra A is quasi-diagonal.
Let me just make a point here. So my point is the following. My point is that, in fact, the statement should be slightly different for this theorem. What I mean is that there should be an if and only if, because the only thing that you were needing in your proof was the fact that the embedding problem was okay for the original C-star algebra. And by Voiculescu's characterization, it turns out that if the C-star algebra is quasi-diagonal, then the embedding problem is okay, almost by construction, because you have this inclusion of A in B omega. So I think there is a slightly different statement from your statement, where you remove nuclear and you replace it by the fact that the embedding problem is okay for A. Then it's if and only if.
One has to be slightly careful for what one means by if and only if, because
of course, you know what I have in mind. But what I have in mind is that certainly from Voiculescu characterization, then it is true that A embeds in B omega, okay, which is exactly the embedding problem. And what I am saying is that conversely, if you have the positive answer to the embedding problem, then your proof goes through, I'm pretty sure, because you were using more.
The problem is, and one very important problem is that when we use Chris-Schaffhauser's theorem, we lift on the level of KK theory, it's very important that either that A is nuclear, or that that A is exact, and that we work with nuclear KK theory.
Okay, fine. So I didn't get that from the proof you were.
No. So I didn't actually tell you how to use Chris-Schaffhauser's result, but really, But you need these generalized version of Voiculescu's theorem, so the Kasparov-Voiculescu type theorem. And for that, we really need some nuclearity to...
I understand perfectly, but what I mean is that my result is only used to have the approximate embedding.
Yes, yeah.
That's
and then we need to, when we need to lift it up, that's when we use the nuclearity.
That's where you use the nuclearity. And very good. Okay, excellent.
Yes. Thank you very much. And then so let me mention so Chris-Schaffhauser actually sharpened this result by showing that, so this was in his follow-up annals paper, that if you pick A and B like we did up here in the proof, then A actually embeds into not just a B omega, but instead you can embed A into B tensor this UHF algebra, this universal UHF algebra here.
So this is where you use the fact that B omega is close to
exactly.
B
yes.
Somewhat.
So by using that B omega is close to B, he can kind of push this down, and that's how he actually gets that not only is A quasi-diagonal, but it's actually what we call AF embeddable. It embeds into this AF algebra here.
By the way, I just have to ask a stupid question about ultrafilters. What I mean is that I presume that you don't use any specific property of the ultrafilters that you are dealing with.
No.
None at all.
No.
But
actually, when we use these results, it's easier to prove them. When we generalize it to more traces, it's easier to work with just the ordinary sequence algebras and have no ultrafilters at all.
I know quite well, but what I have in mind though is that there are extremely special ultrafilters which I used a very long time ago in logics, and which have the properties that I have written, one of my first papers was on these ultrafilters, which are extremely special and which probably might simplify some proofs when you use them, because they have absolutely remarkable properties, which, it's like, it's very much like evaluation at one integer. I mean, and so they are so special that, for instance, when you look at sequences, I mean, you can identify them. It's worth thinking about that. What I mean is that, of course, when you were working with ultra products, you didn't care about what the ultrafilter was. Now, when you write this stronger statement of Schaffhauser, you already have passed from the ultrafilter. So in general, for instance, there is this general fact that if something is true, for instance, some limit is attained for every ultrafilter, then you have ordinary convergence. And I was wondering whether he was using something of that type, whether he was using the possible variability of the ultrafilters.
I don't think he is.
You see, let me give you an example. I'm sorry to intervene, but it's an example which is due to Henri Cartan. So Henri Cartan is the one who invented the ultrafilters. He invented them when he was in Bourbaki, in a Bourbaki session. And then, for instance, he could prove in one line the existence of the R measure on a compact group, just using ultrafilters. But because he had uniqueness of the R measure, he also knew that the answer was the same for every ultrafilter. So he knew from abstract nonsense that what he had constructed was convergent towards the limit. But he was not happy with that. You know, every mathematician is always worried. So in fact, he wrote a contre-rendu note in which he proved by hand the convergence that was deduced from ultrafilters. So, I mean, I just want to mention that because indeed it's a very powerful tool, but it has resources which are, you know, quite hidden sometimes. I mean, these ultrafilters. Okay, I'm sorry to have interrupted.
That was a very interesting comment. Very thankful for that. So let me move on in the title I had classification. So let me move on to what was this big classification result from not that many years back. So I am only mentioning a very small subset of the number of people who really should be mentioned here. So the final pieces were really due to Elliott, Gonglin, and New, and this Tsiguisis-White-Windsor theorem from before. And then if you're looking at the purely infinite case, the one without traces, then there's Kirchberg and Phillips. And the list of names of people who contributed to this theorem goes on and on and on. But let me just state what is the theorem. So the theorem is that if you've got A and B are separable, nuclear, simple, unital C-star algebras, which have two extra properties. So the UCT that I mentioned before, and then this Z stability that I'm not going to go into too many details about. But if you've got this class of C-star algebras, then A and B are isomorphic, if and only if they have the same K-theory and traces. So the classification is really using K-theory and traces. And one thing that's interesting about this new approach that I have with Carrion, Schaffhauser, Tsiguisis, and White is that if you break it down, you can really see where are the traces coming from and where is the K-theory coming from. If you actually look at if you think about what I was just telling you in the previous slides. So let me just try to give you a very rough sketch of what happens, how you would go about proving this if A and B had, say, a unique trace. So if A and B both had a unique trace, what I would do is I would break the problem into two parts. So I would have a tracial part, which is finding a trace-preserving homomorphism from A to this tracial von Neumann algebra. And then I've got a K-theory part, where I take an isomorphism in K-theory, which is compatible with the traces. I argue, as I did in the slide from before, and that actually gives me a star homomorphism from A to B omega that preserves the trace and does the right thing in K-theory. So actually induces this isomorphism in K-theory, more or less. I have, of course, to compose with the inclusion from B into B omega. So this is a vast simplification of what is actually happening. The actual result, this would not at all be enough to conclude classification, but this is just a very rough idea where you can really see how you break the classification into a tracial part and a K-theory part. And the tracial part is solved using Kahn's theorem, and the K-theory part is solved by modifying Chris Schaffhauser's technique to really give us the final classification. So by working very hard from this point on, and actually one needs to be a bit more careful than just inducing the right things in K-theory. You also want to induce the right thing on some more fine invariants than just K-theory. But then you can actually turn this not only into a star homomorphism from A to B, but also because we are trying to classify things, you can actually turn this into an isomorphism. So this is a very, very, very vast simplification of what is actually happening, but hopefully you can get a feel for what is actually happening here, that we're using Kahn's theorem and then Chris Schaffhaus's technique. That's really what is the underlying strategy. So I just want to ask the organizers, how long do I have? Was it until
you still have some time.
I still have some time. Okay, perfect.
Yeah, no, don't worry.
Okay, that's good.
Yeah, okay.
In that case, I can address a few more things that I want to address. So one thing is, what happens if you do not have a unique trace? So now I've got a set of traces. I've got T of B will denote the set of tracial states of my C-star algebra B. What I will do is I will define, instead of this left kernel I had before, I will define something that looks somewhat similar. So I've got this supremum here. So that means that point-wise, I want to take the supremum of all of these two norms. I squared the two norms, but whatever. And then I want to take the limit along the ultrafilter and get 0.
You take normalized trace, I presume. Tau of 1 is 1.
All of my, they're all tracial states, yeah. So they all have norm 1. And then when one tries to run these methods, then the tracial part, when you look at this quotient, you no longer get a von Neumann algebra. Instead, what you get is something that, without going into too much detail, you get something that resembles a bundle of von Neumann algebras. So something that looks like a continuous bundle in a certain sense of von Neumann algebras, of tracial von Neumann algebras, and using, again, Kahn's theorem on each of these fibers. So each possible limit trace you can construct along ultrafilters, you take an induced von Neumann algebra, you find these star homomorphisms, and then you use a certain gluing technique that was underpinning some of the recent work in solving part of the Thomson-Windsor conjecture. You use that to then glue this together to a trace preserving star homomorphism from A to this quotient. So what I just want to highlight is it's still very, very von Neumann algebraic what is happening on this level of finding a star homomorphism. And then the K-theory part is again the same. Chris Schaffhaus's technique actually still applies in this case with this more general thing here. And now the class of C-star algebras that we're allowed to use has suddenly grown to, for instance, include all the classifiable C-star algebras from before. They will always be like allow for Chris Schaffhaus's lifting technique to work, and therefore we can lift this to in the same way as before using the UCT and K-theory. So this is again a very, very rough simplification of the over 100-page proof of this result, but really it is a completely new approach, and I think that what is really happening here is that we've really broken down like how are the traces used in a more von Neumann algebraic way, and then using Chris Schaffhaus's KK lifting technique to then lift this information. So if I still have 5 more minutes, I would.
Yes, you do.
Yes. Then I would like to just mention a different application that is not related to classification, where I've been able to modify some of these techniques to work in a different setting. So just before doing that, I'd like to mention a theorem that fell out of the Seguesius-White Windsor theorem, where Rosenberg proved one implication and Seguesius-White and Windsor proved the other implication, which is that if you've got a discrete group G, then it is amenable if and only if the left regular C-star algebra is quasi-diagonal. And really, well, so what happens is, so Rosenberg proved that quasi-diagonality implies amenability, and then to go the other way, one realizes that amenability implies that this is separable nuclear. UCT follows from Jean-Louis Tu's result, and of course any group C-star algebra has a faithful trace if it's in the discrete case. So what I was trying to do is I was trying to modify this to also work for locally compact groups, and I was able to come up with the following theorem, which is that if you've got a second countable, locally compact, and unimodular group. So unimodular is because I really want to have the induced von Neumann algebra to be semi-finite. Like before, we were using tracial von Neumann algebras, and I've been able to modify a lot of the arguments to the semi-finite setting. And by doing that, I can now handle these locally compact groups. So if one of the following holds, so if G is amenable, G is type 1, or if G is almost connected, meaning that if I quotient out with the component of the identity, then I get a connected group. Then the left regular C-star algebra is quasi-diagonal. I'd like to just try to give a very rough sketch again of the argument, because the idea is the same as before. So this is just the theorem from before. So in this case, the left regular von Neumann algebra is going to be a semi-finite von Neumann algebra with a canonical semi-finite trace, since G is unimodular. So unimodularity implies that it's semi-finite. And the canonical trace is the Plancherel weight. And oh, I should have mentioned, of course, that I forgot to write this, that L of G is also injective. This follows, well, from amenability, it's a classical thing, and the same with type 1, and in the almost connected case is due to Con. So now one has to modify the approach, because we no longer necessarily have any tracial states. So what I can do instead is I can find an AF C-star algebra, and I can find closed ideals in the ultra power. So now, before I only had one ideal, and I looked at the quotient of B omega with J, but now I need to find two ideals, but I can do that in such a way that if I look at the quotient, I don't get a 2 infinity factor, but its multiplier algebra will be a 2 infinity factor. So I somehow still have, before I had some quotients which were tracial von Neumann algebras, but now I can instead produce semi-finite von Neumann algebras, not as the quotients, but as the multiplier C-star algebras of the quotients. So now, again, using Kahn's theorem, I can find a map from L of G into this multiplier algebra that's trace preserving. And I can then, this will then induce a star homomorphism from C star lambda G to this quotient. And now, again, I can modify Chris-Schaffhaus's technique to lift this to this ideal I, which sat inside of B omega. And now I found a star homomorphism from the reduced C-star algebra into B omega. And that's, so again, it's the same underlying strategy that's happening here, that that you're breaking it into first doing some things with von Neumann algebras and then lifting it using Chris-Schaffhaus's technique. So I'd like to end up with a question which I think is a fun question that I thought of when looking at this, which is, if I've got a unimodular group G with an injective von Neumann algebra, is the induced C-star algebra going to be quasi-diagonal? So in all of these cases, it's definitely true. But in general, I don't know if what would happen. So just to mention, the converse is definitely not true in this case. So unlike in the discrete group case, if I take any group and I look at the Cartesian product with the real numbers, then I get a quasi-diagonal C-star algebra for any locally compact group G. But the von Neumann algebra is only injective if the group G was itself had an injective von Neumann algebra. So take any group G that doesn't give an injective von Neumann algebra, and you can produce, if you just take the Cartesian product with the real numbers, you get something quasi-diagonal where the induced von Neumann algebra is not injective. So this will only be an implication in one direction, but I think it's a fun open problem that I would like to know the answer to. But I'm going to stop here. So thank you very much.
Thank you.
Thank you. Yes.
Well, more questions, comments, please.
Yeah, so I have just a comment about the last thing. Indeed, I mean, the last thing, clearly it's related to the embedding problem rather than, yeah. I mean, for instance, this last result of Voiculescu is clearly the embedding problem. I mean, by his characterization of quasi-diagonality, right?
Yeah.
Yeah, sure. Okay. I know that's clear. So this was something which was sort of turning in my mind. Yeah, I just want to add one thing about what I said very quickly about ultrafilters. I mean, the ultrafilters, which are very special, they are, if I remember correctly, they are called rapid ultrafilters. They have the following property, which is extremely strange, that when you take normally when you take ultrafilters, you have to remember how they are indexed. But the rapid ultrafilters have the properties that you don't have to do that. In other words, it's enough to know the image of the ultrafilter in the space in which it is taking place to know its labeling by integers. Which is an extremely strange fact. I mean, you know, it's so it tells you that you can think of the ultrafilter not as a kind of generalized sequence with values in a space, but like as a ultrafilter in the target space. I don't know if this can have any use, but
It's very interesting. It's definitely something I will look more into. It sounds very interesting.
So Ralph has a question, I think. Yes.
Yes, when you did this construction of KK elements, you talked about the map on K here, but not about the thing in X. Can you remind me how that is handled? Why is it enough to lift it as a map on K theory?
So let me just go back to the diagram that I had. Oh, it goes back here. So it's enough to lift this on the level of K theory when you satisfy the UCT. It's essentially because what's going on down here is a von Neumann algebra. So if I can lift this on the level of K theory, I can use if I've got the UCT, I can lift it further to KK. But then when I want to check that it actually lifts what's going on down here, I can use the fact that the K theory of von Neumann algebra
it's injective.
This is a type 2-1 von Neumann algebra.
Yeah.
So it's got injective K0 and trivial K1.
Yes, very good. And have you tried to do something in the non-simple case? So if you have non-simple C-star algebras, then, well, we have some universal coefficient theorems in certain cases. For instance, just an extension of two simple C-star algebras. That might be the first thing to try. Would the technique still work in those cases?
So that is a very hard problem because we would need to have ideal related versions of these Voiculescu type absorption results. So I proved some results of that sort when you've got finitely many ideals or like C-star algebras over finite spaces back quite a lot of years ago. And so we definitely have some machinery that might allow us to do similar things, but the thing is that right now we don't even know what the right trace kernel ideal would be we would also have to be able to handle unbounded traces. So I'm pretty sure that what I was mentioning, what I was hinting at towards the end is the first step in that direction of being able to understand what happens if I'm working with tracial weights instead of tracial states. But all in all, the answer is it's too early to say how easily the approach would be adaptable to the ideal related setting. But it's something I'm thinking about quite a bit.
Mm-hmm. Of course, one could also look at compact or even finite groups acting on things and how you can integrate those in the discussion.
That is also something I'm thinking about.
Yeah, I suppose these are the obvious questions to anybody who is trying to go beyond the existing classification results. Yeah, you could try to test them by doing something which hasn't yet been done. And well, those are the most obvious guesses that come to my mind.
Yeah.
More questions? Okay, so let's thank Jamie for a very nice lecture.
Thank you.
And see you guys in 2 weeks' time. Bye.
Bye.